In the name of God, the compassionate, the merciful, engineering plasticity, Chapter 5, Elastic Plastic Analysis of Bending, Part 5. In this part, I'm going to talk about a spring back again, but for the plane strain conditions. Now for the plane strain case, as we can see here, H relative to B is very small. So we have this kind of beam here which is bent in the XY plane. Now in here we assume plane strain because this plate in the Z direction we assume epsilon Z is 0. Because almost anticlastic curvature is suppressed due to the dimensions of this, because here we have a very wide dimension in that direction, then anticlastic curvature is suppressed and the deformation in this direction is almost 0. So that's why we assume plane strain. It means that we have only a strain in the XY direction. Therefore, if we put Ez is equal to 0, that's the elastic strain. Ez is equal to 1 over E times this relationship is equal to 0. So we can find the relationship between sigma Z, X and Y, and also we could assume that sigma Y also is equal to 0 because the depth of the beam is very small, and we assume that the stress here is negligible. So if we assume that, we put here sigma Y is equal to 0 and we get sigma Z equal to mu sigma X, and that's the relationship we find, and we know that X is equal to sigma X minus mu sigma Z over E, because sigma Y is 0, and therefore that is EX also we know that is equal to Y over RE. Remember that these are the elastic strains that we are considering here. So we could write here sigma X is equal to Y over RE times E, because sigma X is equal to EX. So that is sigma X plus mu sigma Z, because when this is the bending stress is applied, we have sigma X equal to that, okay? And therefore that's Poisson ratio. Therefore sigma X is equal to EY over RE, and here we put sigma Z equal to mu sigma X here. So we take sigma X over there, we get 1 minus mu squared, and that's what we get, okay? Because mu times mu is squared, and if we take that, it becomes sigma X times 1 minus mu squared, so that 1 minus mu squared comes into the denominator. So that's the relationship of sigma X. And what is the bending moment? Bending moment, of course, is sigma X times B times dy. B times dy is the element which we take here, and then B times dy is the area of the element, and times y is the, because sigma times B times dy becomes the force times y distance gives the bending moment. So if we integrate that, we get this, okay, between h over 2 and minus h over 2, because in the middle is the neutral plane. So we get EBHQ over 12 RE times 1 minus mu squared. And instead of E divided by 1 minus mu squared, we write E prime PHQ over 12 RE. That's what we get for the bending moment. Okay, that's the substitution we made here. And again, we remember that we had this ME plastic, the boundary of elastic plastic. We had this formulation. Now we put here E prime instead of E divided by 1 minus mu squared, so that we get this relationship. And in here again I have written the same equation as before. Remember that before we had here the elastic moment due to a spring back, and this is the elastic plastic, which is on the boundary of the elastic plastic deformation. And going again the same procedure as before, 1 over RE is equal to this, and doing more manipulations here, and we know that R over RF equal 1 minus R over RE, because the geometry doesn't change, whether we assume plane strain or whether we assume plane stress. So we can use the same relationship as before, and substituting here, we get this relationship R over RF again, and so we get this relationship this time. So that's the plane strain we have just solved, and that's the plane stress we solved in the previous slides. And as you can see here, we have plotted R over RF relative to RY over EH, okay? And that's what we get here. When RY over EH is 0, R is equal to RF, it means that we don't have any elastic spring back, and here we have the maximum spring back. So as we go through here, as the relative value of RY over EH becomes greater, the difference between these two is pronounced. For instance, here you can see that we have a big difference here, or going like that. Okay, so that is the difference between plane strain and plane stress, but this difference, in my opinion, is not important, because plane stress or plane strain depends on what geometry you have. If you have a geometry that the depths and widths are almost near to each other, then you have to use the plane stress, and you get this. And if they are the other way around, I mean the depths and widths are far from each other, then you have to use the plane strain. Now I have this example for a spring back here, which has a RF is equal to 10 inches. Supposing we have a plate, okay, sheet metal. We have a sheet metal, we want to bend it, okay, just a pure bending. We want to bend it to 10 inches. The final radius we want to be 10 inches. It's a flat sheet of material, and the thickness is 0.03 inches. The yield strength is this, and E prime is this. So if we use those relationships, we get R almost equal to 4.2 inches. That means that if you want to get a 10-inch radius for your sheet, the final radius, you want to change it to a bend section of 10 inches, then you have to use a punch tool with a 4.2 inches radius, because when it bends to 4.2, it springs back to 10 inches. Okay, so that's how we design the tools and molds and dies and punches for the deformation of sheet metal. So far we have talked about spring back and what a spring back is and how we can calculate it for simple cases. Obviously, for complicated cases, we should use finite element simulations and numerical analysis. It's very hard to compute a spring back for complicated cases using analytical methods. Now the question may be that, okay, we calculated the spring back. How do we reduce it, or how do we omit it? Sometimes we cannot reduce the spring back, but sometimes we can. Once we calculate the spring back, then we could design the punch and the die and the tools so that we reach the final geometry that is desired. Okay. For instance, if we want radius of curvature of a certain dimension, then we design the punch so that the spring back is included. Okay. For instance, a sharper radius for the punch gives the desired radius of the bending that we require for the part. But nevertheless, sometimes we could reduce the spring back by applying a tensile force at the same time. This has been shown in this figure here. You see, this is the beam that is under pure bending, like that. That is the cross section of the beam, which has been assumed to be rectangular here, and that is the elastic bending. Okay, so we have some stress distribution which is tensile and stress distribution which is compressive. Let us have a look at the stresses in the case of a spring back. Now, when we load the beam, we have the elastic plastic loading. Okay, we load the beam up to here to the yield point, and then we have rigid plastic model, and this is the yield stress, so it remains constant, and we have this kind of stress distribution up to here and then elastically up to here. Okay, so that's the elastic plastic loading. Some part of the beam has become plastic and some part of it is elastic. Now, when we unload the beam, we take all the load off, but the load is off like that. We take this load, subtract this load from this load. Okay, similarly on the bottom. So unloading is completely elastic. Why we go up to there? Because the stress is there. So that's the elastic stress, because we can't have the plastic stress, and elastic stress is linearly distributed. So when we subtract, we have this much of a stress at that stage. Okay, at the fiber, at the outermost fiber. Okay, so unloading is elastic. That's why it's so bigger than the plastic. So we subtract this part from this part. So what remains here are these. Okay, that one, that one, that one, and that one. But we have to have the right signs. You see, this is positive, but this is negative because we have unloaded, we have subtracted the load, taken off the load. So if these are the remaining of the stresses, we can show it regarding this is because this is negative, this is positive, so we subtract this part from that part, so that's positive and that's negative, so we get the negative residual stress here, positive here, negative here, positive here. So you can see that we have uneven stress distribution across the cross section. Okay, across the cross section we have uneven stress distribution. We can remedy that, we can reduce these kind of things by the method that I'm going to explain now. Now, if we apply tensile stress, like this, a tension on this axis. Okay, if we apply a force on this axis in addition to the bending moment, then this force F on the cross section causes a tensile stress. Okay. So if we add up this together, we have a stress distribution for the bending moment stress and a stress distribution for the tensile force. Then if we add up together, for instance, this plus this gives that. I have, well, it's not to a scale here, okay? So that one plus that one gives the tensile stress. And for instance, here we have tensile stress, so we get that. In here, that is minus, that is positive, so we get 0. So you can see if we add the tensile stress, then we move the neutral axis. If this tensile stress has a bigger magnitude than this, I mean if it is big enough, okay, the magnitude is large enough, then we could move this neutral axis outside the plane of loading, and we will have only tensile stresses. We could do the same thing with the compressive stresses. If this is negative all the way, compressive stresses, having a compression on the cross section, then we could move this neutral axis out of the plane that way, and all the stresses will be negative. Okay, like that. Here, obviously, I have applied a bigger magnitude of tension, larger magnitude, and so I have moved this neutral axis out of, it's gone here. If you move that, the neutral axis is there. So, why did I do that? Because now all the stresses are positive, and therefore when I unload, when I remove the loads and the negative elastic stresses are subtracted from these positive stresses, we would have all the way on the cross section positive stresses. Okay, so that's why I have done that. Now, if in the previous example that we just solved, we only add a tensile strain of epsilon 0.02 to the sheet metal, then we will get R equal 9.86 inch. Okay, I mean, we use the same punch, only add a tensile stress so that we get a tensile strain of that. Then we will get very near to 10 inches. While if we go back to this slide that we had here, this example that we solved, if you remember, we had these dimensions. We wanted to get a bend with a final radius of 10 inches. Now, due to a spring back, we had to design a punch with a very sharp radius of 4.2 inches, so that when we bend the sheet metal, it bends to 4.2 inches. But when we take off the punch, take off the load, it will go back to 10 inches. In fact, in here, if we had used the 10-inch punch, we wouldn't get a 10-inch radius. We would get a bigger radius due to the spring back. But in this case, because we have applied the tensile force in here, we have moved this neutral axis, and so we don't have any we don't have a spring back like before. That's why when we use the almost 10-inch radius punch, we will get a 10-inch radius for the final radius of the sheet metal. Okay, obviously applying 0.02 strain means that we have applied a tensile force here to get that much strain. So you can see there is a lot of difference when we apply this F over A to this bending stress.